This is part 2 of the probability homework video, and we're starting with the base rate fallacy. We've already seen the base rate fallacy in our cognitive biases material when we covered the representativeness heuristic. We saw the Jamie case in that section, and we also discuss it in the text that goes with this homework. Because our first question here on the Jamie case is spelled out in detail in the text, and because the questions I'm going to ask you are fairly simple if you read through it and pay attention to the text in purple especially, all you're asked to do here is count dots to sort of illustrate why it is unlikely that Jamie's a creative writing major, even though she totally fits the stereotype of one. Let's skip ahead to the more difficult questions. So this one is called the famous cab example because this cab example is famous. If you put it into YouTube, you'll find people talking about how exactly this little word problem illustrates base rate neglect, and you can also find a whole Wikipedia page on it. So here's the famous example. A taxi cab was involved in a hit-and-run accident at night. Only 2 cab companies, this is before Lyft and Uber, operate in the city, green cab and blue cab. 85% of the cabs in the city are green, 15% are blue. A witness identified the cab as blue. The court tested the reliability of this witness under the same circumstances that existed on the night of the accident and concluded that this witness correctly identifies each of the 2 colors 80% of the time and failed 20% of the time. So our question is, what's the probability that the cab involved in the accident was blue rather than green, given that the witness said it was? So probability it's actually blue given the witness says it's blue. We have a reliable witness, but not a perfectly reliable witness. And that not perfectly reliable witness says it's blue. What are the odds it's actually blue? When presented with this word problem, many students estimate the probability that the cab is blue, given the witness said it was, at around 80%. The information we're given about the reliability of this witness. But that's a mistake. So they might be focusing in on this specific piece of information, the 80% reliability of the witness, but ignoring the base rate information that very few cabs in the city are blue, and most of them are green, and our witness, 25% of the time, is going to say green cabs are blue. So we need to take that into consideration when we figure out what are the odds it's actually blue, given the witness said it was blue, and it's going to be much lower than 80%. So we're going to visualize that. Let's start by visualizing just the base rate information. Out of 100 cabs, 85 of them are green, and 15 of them are blue. Now this is how often a witness is going to identify each one. So of the 12 blue ones, 80% of the time they're going to say it's blue, that's correct, and the other 3 times here they'll say it's green. Of these 85 green cabs, 80% of the time they'll say it's green, so all these green ones are where they say it's green and they say it's green. But some portion of the time, 20%, they're going to say green cabs are blue. That's what these dark blue things here are. So our next step is to figure out how often the witness says it's blue when it's actually blue. So when it's actually blue, that's these 12 cases. How often does the witness say it's blue? That's these darker blue. So just count these dots. That's going to be 12. Drop down 12. And then here's the calculation that goes with that. Step 4. Figure out how often the witness says it's blue when it's actually green. And this is a crucial piece of information that's important to pay attention to. So how often does this witness say a cab is blue when it's actually green? It's this amount, which is, count them up, 17. Fill in the drop down, 17. And now figure out the probability that the witness says it's blue. Right or wrong? How often is the witness going to say a cab is blue? These dark dots are all the times the witness says it's blue. We'll just add that up. 12 plus 17 equals 29. Get that from the drop down. Okay, we are finally ready to figure out the probability that it's actually blue given the witness said it was blue. So the probability that it's actually blue and the witness says it's blue given the probability that the witness says it's blue. So here's all the times the witness says it's blue. Here's the times it's blue and they say it's blue correctly. How often does that happen out of all the times they say it's blue? So 0.12 out of 0.29, which is closer to 40%. So we're now going to calculate the answer to this question in two different ways. The point of this isn't to do difficult math. I can tell you right now the answer is going to be closer to 40% for the next two questions, but the point is to lay out the different ways we can figure out the answer to this question. So one thing that we can do, and again, the answer is going to be closer to 40%, but that's not really the point. We can construct a conditional probability tree. This can be really helpful. And in the text, I've included a link to a really helpful video on conditional probability trees. So check that out. So think of this dot as our starting point, and this is the base rate probability. What's the probability a cab is blue? 15. What's the probability a cab is green? 85. What is the probability the witness says that it's blue, given that it is blue? 80%. That's their reliability. And their reliability is the same for both colors. Could be that they're more reliable for blue cabs than for green cabs, but they're the same. They're equally reliable for these two colors. So here, the probability they'll say green, say the right thing, given that it is green, 80%. And then here's the 20% not reliable. Okay, so what is the probability that the cab is blue and the witness says it's blue? We multiply the probability that it's blue by the probability that the witness says it's blue given that it's blue. And we get 12%. And now the other one we're interested in is the other time they say it's blue. What are the odds that it's green and they say it's blue? So that's the other bit of the tree we're interested in. Probability it's green and, incorrectly, says blue. Well, there's an 85% chance that it's green and a 20% chance of them saying that it's blue given that it's green, which equals 0.17. So what are the odds, what's the probability that the witness says it's blue? Right or wrong? And that's the probability of these. It's either this or this. These are the two times the witness says it's blue. So we'll add these up. It's either this or this. 29. And then finally, what's the probability that it is blue given that the witness said it was blue? So out of this 0.29, how often do they correctly say it's blue? 0.12. So again, that's going to be closer to 40%. Our next way of calculating this is to think about it in terms of frequencies. Interesting point is that we are much better at reasoning through probability information when we put it in terms of frequencies. This is something that might be important to know if we need to give information to people, whether it's to the public or whether it's to physicians. So in a moment here, we're going to turn to making sense of medical tests, but even physicians have been shown to calculate the wrong probability that a person has a disease given that they've received a positive test result because they are ignoring base rates. When given complicated probability information, it's hard to reason through it. So it turns out if you put that same information in terms of frequencies, we're much better at it. So I think I made a reference here to framing effects at the bottom. The same information can be presented in different ways, and that will influence how we think about it. Well, in this case, it'll influence our ability to get it right. So here's that information in terms of frequencies. 15 out of every 100 cabs are blue. Of these 15 blue cabs, 12 will be correctly identified as blue by the witness. Of the remaining 85 green cabs, 17 of those will still be identified as blue by the witness. Imagine this witness is tested 100 times. How many of the cars will be ID'd as blue? Well, 12 correctly and 17 incorrectly. So 29 times this witness is going to say a car is blue. How many of the cars ID'd as blue will actually be blue? Well, of these 15 blue cabs, 12 of them will be correctly identified as blue. So 12 out of those 29 actually identified as blue, which is closer to 40%. Way easier to think in terms of frequencies. How information is presented matters. So let's apply this to interpreting medical tests. So just as the witness was an imperfect indicator of the color of the car, reliable but imperfect, oftentimes tests for various diseases are highly reliable but imperfect indicators that a person has that disease. So if you've taken a medical test, one thing you might wonder is, what are the odds that I have the disease given that I've received a positive test result? And we need a bunch of different pieces of information to answer that question, more than just how reliable is this test. We also need to know, what are the odds of having this disease at all? So let's reason through a case where we identify base rate probabilities and how to figure out the odds you have a disease given you've received a positive test result. Suppose that the probability that a person in the general population has the disease we're interested in is 1%. That's our base rate probability. And suppose that if a person has disease X, the probability is 80% that they'll have a positive, true positive test result. That means they have it, and 80% of the time their test result will say they have it when they do. If a person does not have disease X, the probability is 10% that they will still have that positive test result. So this time it's a false positive. So now imagine a person who's received a positive test result. What's the probability they actually have disease X? So we've got our base rate. 1% of people have the disease. If you do have the disease and you take the test, 80% of the time it'll tell you you have it. But if you don't have the disease and you take the test, 10% of the time it'll still tell you you have it. Here is a conditional probability tree with this information. Here is our starting point. 1% chance you have the disease, 99% chance you don't. If you're in this 1%, you've got the disease and you take this test, well, you have a probability, the probability of getting a positive test result, given you do have the disease, is 80%. But also, there's a 99% chance you don't have it, and the probability of getting a positive test result, given you don't have it, is 10%. What's the probability that you do have the disease and get a positive result? 1% times 80%, which is 0.8% or 0.008. What's the probability that you don't have the disease, but you still got that positive test result? 0.99 times 10% equals 9.9%. So now, just like in the cab rate example, we're interested in the probability of a positive test result, rightly or wrongly. We're going to add up those two numbers. The probability that you've got it, and that's why you got the positive test result, and the probability that you don't, but you got a false positive, add those up together. Here is the probability you will get a positive test result, rightly or wrongly. And so then here is the probability that you've got the disease and got that test result over the probability of getting that test result. So divide these two numbers, and you get not closer to 70%, but closer to 7%. So now let's do this same question in terms of frequencies. Unfortunately, I only have 15 minutes of video time, and I've run out of it. I think you'll find the frequency problem to be much easier. The final question is just a variation on this one. So good luck with that, and feel free to reach out if you have questions.